And so I've changed a little bit the title of my talk because I like to discuss, and this is a kind of disclaimer also for the nuclear structure community, that I like to discuss what we understand as nuclear shapes from mean field and beyond mean field perspectives. And before going to the last part of my talk, that will be the calculations, the recent calculations for A96 isobars. Okay, but most of the things that I'm going to present here probably is too basic for many of you, and I apologize for that. But I hope it will help also to clarify some of the things that probably I will discuss during the talk and also during the discussion session. So let me just jump to the. Why?
I have to click on the screen.
Okay, good. So this is the outline of my talk. So I will give you a brief introduction, or maybe not that brief, about nuclear shapes, and something that already was discussed by Magda yesterday. And then I will comment on how we define properly the shapes in microscopic theory, which is the Hartree-Fock-Bogoliubov theory, or extensions of Hartree-Fock or BCS, which is this mean field approximation. And then I will talk about the beyond mean field approximation. So first symmetry restoration and then configuration mixing. And this is something that I think it was already discussed by Benjamin, but nevertheless, probably it is not a bad thing to repeat things. And then I will talk about the results for this projected generator coordinate method for ruthenium 96 and zirconium 96 with two approaches. First, with including triaxial quadrupole deformation, and the second approach is this calculation with including axial quadrupole and octupole deformation. Good. This is something that probably was already commented during this workshop and program. So for the nuclear physics community, the intrinsic shape of the nuclear states is not unobservable. So it cannot be observed directly. And it's inferred somehow from the spectrum, or from the spectra or several nuclei, not only from the energies, but also from the transition probabilities, for example, as we discussed yesterday thoroughly. And but here I show you just a simple picture where you have two different nuclei with a very regular pattern in the spectrum. For example, this xenon 138 or neodymium 152, where you have this 0, 2, 4, and 6 regular pattern with equal spacing between the levels here. And obviously, this remains as a vibrator. And here we have something which is non-harmonic. It's more rotational-like with this JJ+1 law, no, of excitation energy. So by comparing, let's say, these measurements, these are measured in the lab with some underlying models, like this underlying model for some vibrator or some rotor in the system, then we can say somehow that this is intrinsically spherical shape, which is doing quadrupole vibrations, and in this case, this is a deformed object that is doing rotations. Okay, and this is what how we predict or how we extract the intrinsic shape. Yes.
On the left diagram, they are equal space, but not exactly.
Yeah. So this is
a mixture of things.
No, this is again because I mean, so this is the simple picture of just a vibrator is breaking down somehow. So nature is doing whatever it wants, and now the way we describe it can be either a vibrator or obviously. It will be more complex.
It's not harmonic. It's still a vibrator. It's not a harmonic.
Yeah.
It's not a simple harmonic, but still.
Yeah. So if you extract the moment's inertia, is this moment inertia is
Yeah,
equal to a rigid router. When you see this kind of spacing,
in this
yeah,
case, for example, yes, you can
will be
extract,
very close.
but to extract the moment of inertia, then you have to invoke a model.
Right. But suppose you invoke.
Yeah, the rigid rotor model or the JJ plus 1 divided by 2 the moment of the inertia. Then in this case, as George was mentioned yesterday, so it is in between the rigid and the complete super and near rotational fluid.
No.
You can see that the moment of inertia increases.
And yeah, also from here you can extract that the moment of inertia is not constant along the.
Okay, but in the case where uranium, for example, is very constant, but if you extract moment inertia, is that always smaller, a little bit smaller than the intrinsic moment inertia, right?
Yeah.
It's still a little bit smaller.
Okay, so this is also some examples for octupole degrees of freedom. And these octupole degrees of freedom, for example, here this molecule, it's Cl, so hydrogen with chlorine. It reminds that these molecules is doing rotations about an octupole deformed shape. And also we can have also this kind of patterns, this positive parity bands interleave with negative parity bands in nuclei, as we can see here for this radium and these radon isotopes. Okay. Again, so whenever you see this pattern, then we could say, okay, we have an octupole deform, either rigid octupole deform, or it is doing some vibrations about the octupole degree of freedom. Okay. But again, this is something that we have to compare with models. It's model dependent, and these are our measurements, and we interpret this data as if there is something with a given shape. Okay. Then classically or semi-classically, we normally invoke these collective models to describe this kind of collective structure. And these collective models, this is probably the most simple way to describe some collective models. Here we parameterize the nuclear radius in spherical harmonics, and then we expand this radius in different multiples, and then depending on the shape, then we will have quadrupole shapes, octupole shapes, and so on and so forth. So, for example, it is true that, for example, the dipole vibration, for example, is not existing except so as a whole, because it is like a center of mass movement, and this is not giving you any excitation energy, except the dipole is protons against the neutrons, and then you can get some excitation energy out of it. But the first term would be the quadruple term, and so on and so forth. So this is the way we parameterize the nucleus as a macroscopic object. So we don't distinguish protons or neutrons. So our degrees of freedom is just a given macroscopic object with this radius. Okay.
Can you say something about the C of alpha?
Yeah, this is just something to, let's say, in the simplest model, you have this is one or some parameterization just to, you mean this one?
Yeah, yes. Just want to get, I mean, so if you just think of this as a parameterization of the density, then
it is
then if R0 is a free parameter, then
to get the
it's
volume,
just a free parameter,
yeah.
but there must be some model where like you keep R fixed and change alpha and that changes the radius, like other like models.
Probably this is related to also to volume conservation and so on.
So when you change R0, when you change alpha, that
you want to keep the same one.
Yes.
But this is linear expansion, so you can demand over the second order terms.
Yeah. Okay. So you can complicate these collective models as you want, but the key point here is that you consider the nucleus as a macroscopic object with a given radius. So no more protons or neutrons anymore. Then from here, of course, we know that this is the lowest order here for the quadruple is just and the simplest is the axial quadruple shapes with these shapes, and we can have other shapes like this avocado pear-like shapes or these potato shapes or whatever. So this is really nice. And then of course we have this the fruit store of nuclear physics is basically this. Okay, so then the question is, can we describe microscopically this kind of collective phenomenon? And this is the aim of my talk, and the aim probably of Benjamin's talk and Vitek's talk, etc. So if we can, from the degrees of freedom from nucleonic degrees of freedom, let's say from neutrons and protons interacting each other, can we describe these kind of things? Yep. And this is I'm going to discuss this for the rest of the talk. So first of all, then we have to solve the nuclear many-body problem, and this nuclear many-body problem is understood as a problem to solve the Schrödinger equation of a system of protons and neutrons that then interact in each other, and this interaction in principle is not known. So we know that there are ab initio interactions, nuclear-nuclear interactions, or thin-nuclear interaction, etc. And we have also some other more effective interactions, more phenomenological, less phenomenological, etc. But I'm not going to talk about the complexity of the nuclear interaction itself, because this is another field of research. And I'm going to assume for the rest of the talk that we know the nuclear interaction, whatever it is. Okay. And we have the interaction between our constituent particles of the system, which is the nuclear-nuclear interaction or three-nuclear interaction, etc. And then the problem is to solve this Schrödinger equation. And solving the Schrödinger equation is also a problematic thing. So we have on the first, on the one hand, we have the explaining the dimensionality of the many-body Hilbert space. So as soon as we increase the number of particles in our system, then diagonalizing this system is almost impossible. So we cannot solve exactly the Schrödinger equation in the general case. And then also there is another problem. It is how we store or how we evaluate the interaction itself in the two nucleon, or sorry, the two-body matrix elements or the three-body matrix elements, etc. This is also difficult to implement in our codes. How to store these kind of elements that define the interaction between the nucleons. So there are in principle, so we need to solve the Schrödinger equation. And then in order to attack these two problems, there are basically the most widely used solutions to attack these problems are these two. We have either the balance space shell model, or if we are in very light system, we can also use a no-core shell model. And also we can invoke approximate methods like the variational method. And this is where I'm going, the field I'm going to talk about here. Nevertheless, let me say some words about the balance space shell model calculations. In this case, what we have is a system. We reduce the system in this way. So since the system is very complicated, the many-body system, then we can extract from, or we can kind of impose some model of the system in this way. So we can have, instead of having a system of A particles, we have a system of A minus A prime particles, where A prime particles normally is a magic nucleus or a double magic nucleus. And then what we have is just the remaining system is what we call the balance space. So we have a core of particles that is inert, and this core of particles normally is made of some magic or double magic nucleus. And then the rest of the particles are the ones that are interacting, and these are the ones that define the properties of the system. Yes. SRG is similarity renormalization rule. So it's a way of extracting effective interactions from a more ab initio interactions. Yes.
So what's
So would the balance space model automatically generate moment of inertia where it falls as a perfect?
Yeah, this is the problem. So in this case, the intrinsic frame is not well defined. So we have a kind of spherical core, let's say, and then we have the balance particles that are interacting with each other, and this defines a kind of deformation in the balance space. If you want to take into account the full deformation of the system, then you have to take into account also some kind of core polarizations with some effective charges for the mass, for example, or for the charge of the products. So this is precisely one of the things that I wanted to say, that the shape is something which is model dependent, even here.
I think that in the shell model, can they deform the core and still consider?
You can use a deform shell model calculation, and then you have some deformation in the core. But I think it's a way of it contains the same phenomenology as the spherical shell model. It's another way of expanding the wave function.
So how do you imply like one should not trust too much the study of deformation using the shell model, or
yeah, it contains some limitations. Yeah. So it is not the shape here is not well defined, absolutely well defined.
I mean, in principle, you could adapt your operators to your balance space, but it's rarely done convincingly. And you can transform quadruple operators to be adapted to your balance space. Not sure it's
so the thing here is that you can basically you reduce the problem to a balance space problem, and then in this case we can do the full diagonalization of the problem. So in this case we have exact wave functions and exact energies from solving the Schrödinger equation, but the Schrödinger equation obviously is an effective Hamiltonian defined in the balance space. And the way we do that normally is in this way. So we expand our states of the Hamiltonian, so the wave functions of the system are expanded normally in this Slater determinant basis, where it is you have some orbits, spherical orbits, and you can build the basis in this way, in the normal way that we know from our basic courses in nuclear physics. So this is the way we do. And then since this basis can be huge, or indeed the basis is actually huge, then these diagonalizations involve gigantic Hamiltonian matrices. Okay. But nevertheless, it can be done for certain balance spaces and nuclei, not far away from shell closures, but it can be done, and it provides the best. In fact, this method is the one providing the best comparison with the spectroscopy from the experimental point of view. Yes.
And all these bases run over all combinations, all possible combinations of the states.
Yes. Yeah. It defines the full many-body Hilbert space in the balance space.
But when you describe the spectroscopy data, is this close to the shell, close to the double magic? Right?
No, even
work for the
for not that far out, not very far away, because the configurations then will explode. But they are not just one nucleon or less or more than a magic nucleus. It's within the balance space. This is the best method to provide, let's say, a comparison with the data for spectroscopy. And similar methods are the ones are used also by Takaotsuka, etc., with more balance, with larger balance spaces, because they do Monte Carlo sampling in this for these configurations. Okay, but
This agreement is achieved by some fitting, or this is automatic?
so the fit comes in the definition of the effective Hamiltonian. So once you fit once you have your two body matrix elements and also the single particle energies in the basis, then which is the parameters defined in the effective Hamiltonian, so the balance space Hamiltonian, then this Hamiltonian can contain some phenomenological parameters that you have to fit. And then once you have this, then you use this Hamiltonian for the rest of the balance space nuclei, and then there is no.
But the fit is done for the region where you're interested in, right? Or you fit in some other.
You have different, yeah, exactly. You have
Okay.
different interactions for the different regions. So,
Okay.
yeah. And the thing for this SRT evolve is, or the goal for the SRT, for example, is to get from just one ab initio interaction some method to provide effective interactions in the balance space. So, and then this is less parameter dependent. So you don't have to fit more parameters than the parameters that are already fitted in the initial interaction.
So two-body Hamiltonian means two-body.
Two-body Hamiltonian means that you consider only the interactions between two bodies, but not three-body or four-body, etc. Which is not normally is not enough for ab initio calculations. Just you need to include also three-body, at least in for ab initio calculations. Okay, so this is just a few words about the shell model. But then let me talk about the rest of my talk. I'm going to talk about these variational methods. And as you know, the variational methods are based on the variational principle. I like this this way of thinking of the variational principle. Like, okay, so you have the first thing that you have to do is just to define your variational space of wave functions. And then this is the big sack of wave functions that you take out some wave functions out of this sack. You put it in a Hamiltonian machine, and then you get an energy. And then you put another one, and you go to the Hamiltonian machine, you get another energy. And you compare these two energies, and if this energy is smaller than this one, this is variationally better than this one. Eventually, you will take out from the sack one wave function that minimizes the energy within this sack, and then this is the variational approach of the. No, so this so this is the way it's done. And then obviously, depending on how we define this sack of variational space of wave functions, then we will have, if it is the full variational space, then the problem of solving the Schrödinger equation, either from diagonalization or from the variational principle, is equivalent, and then you don't gain anything from it. So you have to reduce this variational space, and if you just restrict yourself to some specific form of the trial wave function, then you have the Hartree-Fock method. So you can extend this Hartree-Fock method by enlarging the variational space, and then you have the Hartree-Fock volume. And then you can these two can be also enlarged by doing some configuration mixing, and then you have this bigger sack than these two. Okay. Obviously, this sack is contained in this sack, and in this sack is also contained for this.
So is this used just for ground states?
Yeah, but you can also use the variational principle for excited states.
I've seen it for excited states, and I was a bit confused because it's
yeah. But normally you first solve for the ground state because you are minimizing the energy, and then you impose some if you want to use for the variational principle for excited states. You impose the orthogonality to the ground state, and then you.
I see. So you should for the minimum.
You should apply it state by state.
But when you do the configuration mixing, you also have a diagonalization, such that
yes,
you will obtain a spectrum in of states, not only overall state.
Yeah,
so the reference states are not necessarily optimized for the excited state, but they are there.
Yeah. So I will come to this point as Benjamin mentioned afterwards. So, but just a matter of language, I'm going to talk about, so I will define Hartree-Fock and Hartree-Fock methods as mean field approaches, and everything else is just a beyond the field. Okay, good. Then let's start by defining or describing a little bit the Hartree-Fock method, because this is what we call the self-consistent mean field. And this is precisely where the nuclear shapes are well defined. Okay, so in this case, we start with our Hamiltonian written in second quantization as usual. So we have these operators that create fermions and annihilates fermions in a given state, and these are completely arbitrary. This is an arbitrary basis of a one-body Hilbert space. And of course, they are fermions, so they are fulfilling these anti-commutation rules. And these are the matrix elements for the kinetic energy. And this is the matrix elements, the two-body matrix elements for the interaction. And here, in principle, one could add three-body interactions with three operators, creation operators, and three annihilation, and so on and so forth. But we normally, this is complicated enough to stop here. And this is precisely the two-body matrix elements I was mentioning before. In the shell model, these are the ones containing, let's say, some phenomenological things. Okay? And not only in the shell model, but also in other approximations. So now what we have to do is just to, since this is basically impossible to diagonalize, this Hamiltonian is so complicated that we cannot diagonalize fully this Hamiltonian, then we invoke the variational principle. And then if we want to invoke the variational principle, we have to define the exact of wave functions, of trial wave functions. And this is precisely this kind of wave functions, this phi. These phi are just the product of these annihilation of operators, beta. And these the beta dagger are in fact the so-called Bogoliubov quasi-particle operators. Okay, so this is the way we define the trial wave functions. Okay, and these quasi-particle operators is just the most general linear transformation between creation and annihilation operators. Okay. And our variational parameters, obviously these operators, these quasi-particle operators are also fermions. And our variational parameters now are these U and V coefficients of this linear transformation. Okay. So this is how we apply the variational principle to solve this Hamiltonian using this simple form of the trial of the Hilbert space or variational space. Okay.
What's the minus state?
Which minus? Ah, this is the vacuum.
So why do you call it minus? What's the significance of the minus sign?
No, it's
Nothing
just
there.
Is it a dash or minus?
It is it's zero if you want. It's the true vacuum.
So the Q is just a quantum numbers, the sum over.
Yes, these are quantum numbers. These are this, let's say this here. States. These are the single quasi-particle states.
But that means you have many parameters.
Yes, these are the parameters. Yeah, so these are the matrix elements of these matrices, U and V, which are in fact they are related because you have to fulfill these anti-commutation rules also for this, and this imposes this orthogonality condition for the U and V's. So they are not independent. These variational parameters are not all independent of each other.
The basis itself is something standard like harmonic oscillator.
But you can use anything. Here,
Sure.
here you can use whatever, but for nuclear physics, is better to use the spherical harmonic oscillator or versions of a harmonic oscillator, because naturally you have the magic numbers for it.
All those one people also, I mean, you have several schools, you have the big schools like the spherical harmonic oscillator, but also people work in Cartesian representation in space.
Yes. Yes.
So do you break the symmetry?
Yeah. So I will talk about this right in a couple of slides. Okay. So this is the thing, no? And well, this is this transformation already breaks one symmetry. and it's the fact that this transformation does not preserve the number of particles of the system. So because we are mixing a creation and annihilation operators, and this is a nice trick to some questions or not. So this is a nice trick to include, in fact, pairing correlations in these simplified wave functions. Yes.
So with so many variation parameters, is it guaranteed that things converge to a unique solution?
No, sometimes you get some minima that are not the absolute minimum. So but then if you have a good method to find the minimum of the system, then you can get a minimum.
You never find degenerate minimum?
You
You never find degenerate minimum, more than one?
Okay, you can get some degeneracy, yes.
They must be because, right?
Yes.
Shape is oriented this way or that way.
So this is the way we solve the way we define our variational space, and then as it was already mentioned here, this transformation is breaking the particle number symmetry. Therefore, if we want to do if we want to describe a LED 208 and not, I don't know, LED 208.6, then we have to impose in the minimization of the energy that we have with these wave functions, with the wave functions that are the vacuum of these operators. We have to impose some auxiliary conditions by the usual Lagrange multipliers. So in this sense, we have this, so we minimize the energy coming from this, the energy functional coming from these wave functions, the HSV wave functions, but this minimization must be done with these constraints. Otherwise, we will have some meaningless number of, at least in mean value, number of particles in the system. So if we want to be sure that we are computing the nucleus that we are interested in, then we have to impose at least that.
But you're still doing a bunch of nuclei. I mean, you're not. This does not make n a good quantum number.
No, it's not. It's not.
Yeah.
So these are not the eigenstates of the particle number operators, but in mean value we have the same the number of particles that we are interested in, but only in mean value. But these are not the eigenstates of the particle number operators. In fact, they should not be. Otherwise, we could not describe, for example, superconductivity in this. Because if they are, with this transformation, if we have a good particle number symmetry, then we collapse, let's say, to the Hartree-Fock solution.
That's a very nice question, but your Hamiltonian conserves particle numbers, so
yes,
the eigenstate of the Hamiltonians are also eigenstate of the particle number.
Yes.
So it's only because of this variational principle that you have.
Yes. So we are, with this trick of breaking symmetries, we are enlarging the variational space, but keeping a very simple form of the wave function. So this is the usual trick.
So you said that basically you want to make sure the mean value converges to the actual neutron and proton number.
To the one you want to compute.
But
so you choose, for example, I want to compute the LED 208. Then I have my two-body interaction. So this is not changing. And then I just minimize the energy of the system with these constraints. And here I will put 126, and here 80. Here.
But that means if you calculate two-point correlation function, they're actually a variance, right? You in the number
Of course.
So in a sense, there's still fluctuation in the
in
the
this
number of
in these wave functions. If these are not eigenstates of the number of particle operators, we will have fluctuations.
But this fluctuation is artificial, right? It's not real. So
yes,
what this I mean, will this be cause some asymmetry in those?
Yes, then we have to correct this And this is the next
Oh, you have
step.
to apply correction.
This is the next step. This is the symmetry restoration that I will talk just in a couple of slides.
Okay.
Okay, so, but here the thing is that you can, so if this is clear, I hope, then you can also extend this concept of these Lagrange multipliers and this minimization with constraints to force the system to have certain parameters or certain collective variables. Okay. So in a way, in the way we describe the variational principle of this definition first of the SAC, here what we are doing with this minimization is just that from this SAC, we are just minimizing the energy in a smaller SAC that fulfills these conditions. Okay. So we are doing a restricted variation because we are just selecting the Hilbert space that fulfills, apart from being an HFD state, is an HFD state that fulfills these conditions. Okay. And this is precisely here we can say, okay, so let's take these parameters. These are the so-called collective coordinates. And we can take, for example, the expectation value here of the quadrupole moment operator. Or we can take the expectation value of the octupole moment, or some pairing degrees of freedom if you want, or some other operators that you can imagine. So this is where the shape enters into the game.
One more question. So how you have a proton neutron, right? So will this interaction between proton and neutron still will be automatically included somehow?
Yes. Yeah. So this you have here you have the protons and the neutrons there, and then you have these transformations are also includes this mixing these quantum numbers. Normally you get the total wave function normally is factorized in protons and neutrons, and then whenever you have here a quasi-particle which is a proton, is made from protons here only, and the other way also for neutrons. But nowadays, for example, with Taurus, that I don't know if Benjamin mentioned, well, there is a new code, and there are some other codes also that can mix protons and neutrons here in this transformation. And for example, a proton quasi-particle is not only made by proton particles, but also by neutrons. And by doing so, we can include the so-called proton-neutron pairing in our formalism.
They are coming from the two-body interaction, right?
Yes.
So
the interaction is the interaction, and the way we explore this interaction with these approximate wave functions is another story.
Yeah. So you said the quadrupole operator and or any kind of
yes, here
multiple.
Yes.
And you have input from experiments.
Not necessarily. So this is something that we can say. Okay, so let me go to one slide here. So then what we can do is this. Okay, so let me. So I want to take magnesium 24, 12 protons and 12 neutrons, with the Gogné interaction, which is a normal and standard nuclear-nuclear interaction. And then I will solve this, let's say, Hamiltonian, although it's not a Hamiltonian, but let's call it like Hamiltonian. And I'm going to solve this Hamiltonian using the variational principle with Hartree-Fock-Bogoliubov approximation. And then I'm going to compute the minimum energy for a given value of the quadrupole moment. Mm-hmm. And this is the curve here. So this curve is the minimization of the Hartree-Fock-Bogoliubov energy imposing a given deformation, quadrupole deformation in the system.
Okay, and this so this given deformation is taken from experiment.
No.
Sampling all the space, right?
It's just it's the way we parameterize the wave function.
So it's a prediction from the theory.
Yes, in this case we could say, okay, so this is the minimum of if we would do anything without any constraint, then we will end up to this point because this is the minimum point.
So with that Hamiltonian that you have chosen and that set of back of states,
Yes.
This is the minimum value.
Yes, that's right.
But
That's
is this beta minimum is actually very close to the quadruple constraint you put in, or they are?
No, the quadruple constraint is this. So this is something that is forced.
We probes all the values of the.
We are changing the value. So let me go back here. So we solve this equation. So this equation here.
Yeah.
So we minimize this energy, and this energy is built in this way. And we force these wave functions to have this beta or Q to 0, for example, the quadruple moment.
Yeah, but that's
And we change the quadruple moment step by step, and then we
but this
have
is small q. This is the beta minimum, always the corresponding to the beta minimum.
No. It's the full space. So
But
you
that
can
number is fixed or not fixed.
No, and
this for each calculation is
horizontal
fixed.
axis.
Yeah,
Yeah.
each point in the plot is
Each
fixed, but
point.
then you scan the
So let me this.
Oh, okay.
x-axis.
So
Okay,
we are
yes, yeah.
computing in different points. We are computing the energy that minimizes. So we minimize the energy for these different
Okay, I
points.
see. So this is a continuous set of wave functions that you
Yes.
use again to even.
Although it's
use later.
discretized because you don't.
So maybe to expand on your question. So everything depends on the energy functional, and the energy functional typically has a dozen parameters, but it's the same parameters everywhere in the nuclear chart.
Correct. Yes, there was another
So
question.
I have a question regarding the Q or the.
Yes.
The associated Lagrange multiplier. What is the dimensionality? Is it just the overall deformation and you apply it for every?
So this is just the operator. This, for example, here, this is r squared y to 0.
Okay, and it's just global because. I
Yeah,
would
the mass,
imagine
the
that
mass.
just like for different like single particle states, you could have different deformations.
No, but this is for the whole many
whole,
body
just
system.
one.
Yeah.
Okay.
Just to verify, so if you left it completely unconstrained,
Yes.
you got a
Then,
minimum,
then,
and
then
then
you
and then
end
calculated the average
then you
beta,
end up
you would
here.
get, you would get exactly that average beta, right? At the minimum.
Here,
You
yes.
get one or the other.
There's another.
Or this one, if you are unlucky, and then you start from some seed wave function of your
But that means it was a
calculation. And,
mistake, you didn't really get the minimum, right?
yes, that's why also it's useful to explore these degrees of freedom, because sometimes you have this secondary minima, and then it is better to explore the
In the second minimum could correspond to some real state.
yes,
Some excited state.
yes. In this case, it's not, because it's a saddle point in the gamma degree of freedom. But I will come to it later. But here it's you see that, and this is the first step of our calculation, and this is where the nuclear shapes are well defined. Okay. I hope now it's clear.
I was wondering, can you calculate the variance to see how good this approximation is?
Yeah, we can do it. It's the problem with the balance is that we need to compute this h squared, which is a 4-body operator, which is
very
horrible,
tough.
and it's hard. But we did it in people in Monte Carlo and model.
Yeah.
And this is the best way to.
But the energy functional is not a Hamiltonian, so.
Yeah.
You have to ask what it means.
Yeah.
to square.
Yes.
So when you said this has well-defined deformations, I'm puzzled because you're not constraining any of the other Q components.
Yes.
Which means that
That means that all the this is
you
all
only,
this
you
is
only,
something that I wanted to comment on.
you only constrain one
Yes.
particular component of the
Yes.
deformation.
And the rest is free to do whatever they want. And they adapt, they minimize so they adapt themselves to minimize the energy. Yeah, that's a very good point. Yeah. So here it is not just a quadruple deformed state. So you have quadruple and all the possible multiples. But the all possible multiples will be surrogated from of this. Okay.
Okay. Can't the wave function have contribution? So this is like an expectation value of the quadruple moment, right? Is exactly this value. But
Yeah, so
your,
this
your
is-
wave function could be a linear superposition of states that have different quadrupole,
no. The quadrupole is fixed.
the expectation value.
The expectation value, yes.
So can't it be a linear superposition of states that each have a
You
different
can
quadrupole?
compute.
And you just take the expectation to get this value?
So you can compute also the moments of the quadrupole operator and so on. So you can compute the fluctuations.
Yeah,
in
exactly.
Q.
So
This is
even the
also-
quadrupole isn't necessarily fixed, even at this minimum point, right?
Yes, but the fluctations normally are small in the operator that you are constraining.
Okay.
So, so if you take 1 point in this curve,
Yes.
you can then ask what is the energy minimum along other deformation axes.
Yes.
If you go back to your formula, would you, let's see if you also consider.
You can
other
include
deformation,
as many
you add just add the additional
as
terms.
many as you want. And if the system is not, if you don't torture the system, then it will get some minimum.
So
you
right now,
will get some solution. Yes.
right now the gamma degree is not considered, right, in this particular.
In this particular case, I will come to it. Yes.
Yeah, so why do you have to use discrete values of the quadrupole or of the beta value?
No, because you solve one equation per value of beta, so you can, I mean, so you can discretize this with a smaller.
Right, I understand, but you said that all other multiples.
The other multiples are just adjusted to how they want to be. Because, for example, in this, I don't know if you can distinguish here, but probably if you look, so this is probably here you can also see some hexadecupolarity, but it's not really well done, defined. But so you can compute the expectation value of other multiples and see what is the expectation value of those. And that would be the self-consistent hexadecupole deformation. So whenever you are here, this is the minimum of your Hartree-Fock-Bogoliubov, and then you can compute all the multiples you want, and these are the multiples that minimizes the energy.
Yeah,
the
I
total.
understand, but why can this one be treated as same as all other multiples?
Just
No,
an
but-
example.
Yeah, it's just an example.
But in practice, you can do
Yeah, you
several
can.
of them at the same
Yeah.
time.
You can do as many as you want, and this is what I want to.
Yeah.
For example, now instead of having only axial quadrupole deformation, you have quadrupole deformation, the Q20 and axial, and Q22 that can be parameterized, as you know, by beta and gamma. And this is the beta gamma plot. So these are the energy surface as a function. Again, so this plot contains many points here, and this is just the continuous interpolation between all these different calculations for the Hartree-Fock-Bogoliubov constraint equations. And you see first the fact that you have this symmetry, you have the six sextants are equivalent, because this is just a matter of, so since these deformations are essentially the same as for gamma equals 0, essentially the same to gamma equal 120 and 240, and for the oblate shape the same, then you have this equivalence between the six sextants here in the beta gamma plane. Okay, and you can move from, for example, what is the triaxiality here is just this. You are moving around the clock. And yes.
So all the calculations are discrete that you
Yes.
choose. So you have several variables, and you
Yes.
can. So it's just multidimensional walking through the space,
Mhm.
the common space.
Yes. And then if we have this static picture, then finally we don't need to include all these states, because these states are basically equivalent to only this from 0 to 60. And this is what normally one does. Other degrees of freedom that can be computed, for example, in the axial case, we can constrain to beta 2 and beta 3. This is beta 2 is again the quadrupole, and as soon as you increase the value of the quadrupole, you get from, let's say, from oblate shapes to spherical to prolate shapes. And if you increase the value of beta 3 starting from there, then you get this avocado or this pear shape. Okay. And you see now in this case, the minimum of this example, the barium 144, the minimum is here. It's a kind of static octupole deformation. Not very large, but still the minimum is there. Okay, and you have some fluctuations here in the beta 3. But just for the mean field solution, we have only the absolute minimum is here, and that would be the one that minimizes the energy at the mean field level. Okay, and this is precisely what they define, the shapes are defined here from the microscopic point of view. So these are made of the interaction, made by the interaction of protons and neutrons in the system. And this is something that I wanted to tell. I think this is, okay, yeah, this is all for this. So with this, for example, we can do the typical studies that we can do is what is the shape evolution along isotopic chains. No, this cadmium, these are boring because you go from the shell closure n equal 50 to the shell closure n equal 82, sorry. And you see the evolution that the system starts from being spherical, it becomes deformed, and then it goes back to the sphericity in this case. Okay. This is the typical behavior of a boring isotopic chain, like this. Okay. Then you can go to other isotopic chains, for example, the krypton, that also Magda was mentioning yesterday. And here, in this case, the energy surfaces are richer, so, or more complex. So here you start from, for example, for krypton 70, you have an oblate minimum here, and then the next one, the krypton 72, you have two coexistent minima. Then you have krypton 74, you have also coexistent minima here. You can find several minima in the energy surface. Then you reach the n equal 50 shell closure, and then you have the spherical state or minimum, and then you have this evolution. Okay, so you have all these minima appear in the energy surface, and then this is how normally we interpret whether we have shape coexistence or we have shape mixing or these kind of things. Okay.
This is before the symmetry restoration.
Yes,
right? So
this is just pure field, and these are the shapes are well defined here. This is the mean field is the wave functions that define the shape.
So when you talk about shape mixing, where do I see that? Can you show an example?
I will, yeah, shape mixing would be something that you have a very shallow minimum, and then in principle you have the several configurations would be the minimum of the system.
Okay, but the method still gives you a minimum.
Yes,
and that's
shape mixing here is not even well defined. So
but when you see it's such a shallow minimum, then you think that you might have to do more in order.
Yes, that's right. That's correct. Yeah.
You basically never have large fluctuations at one point in the shape. Fluctuations only come from the.
We can compute that, but I think since we have to restore the symmetry and mix everything else afterwards, then we can. And this is what they're coming next. I don't know. Totally out of time.
Yeah, totally. But this, we will. If we cannot finish, we'll.
Okay, so just stop me whenever you want. So it's. So I don't want to bore you.
No,
okay, so this is the krypton, and also this is a nice view because these shapes, in fact, can be related. The shape of the energy surface is also related to the underlying cell structure of the nucleus. So here, I don't know if you're familiar with these Nielsen-like plots, but this is just what we call Nielsen-like plots, but these are self-consistently calculated. So this, if we go so this is the quadrupole moment, okay, for protons and neutrons. Well, the single particle energies for protons and neutrons. And these are just, if we go to the beta equal to 0, then you see the shells, the spherical shells that are with the full degeneracy in MJ. Okay, so if you have J equal 3/2, then you have MJ can be either 3/2 or 1/2. No, so this is the full degeneracy is here, and you have the spherical gaps there, and these shells, these single particle energies, are calculated self-consistently from the Hartree-Fock-Bogoliubov wave functions. So
you take the trace over beta 2 with keeping beta 3 0 or fix that?
No, in this case, these are just actually quadruple deformed, no octuple whatsoever.
So you go along the lower horizontal axis of your previous plot.
Yes, that's right. Yes. So this is beta 3 equals 0.
And this is from your calculation, right, that you showed earlier?
Yes. So this is in fact going from, I can show you, going from here, well, from here to there, and nothing here. Okay. And then from each point, we can compute this underlying shell structure. And these are just the one body, the energies associated to the one body Hamiltonian, which is something that you compute self-consistently from your wave functions. So once you have the wave functions and you have the two-body Hamiltonian or the two-body or the energy density functional, then you can compute this single particle structure. Okay, as a function of beta 2, prolate and oblate. And here, this is the Fermi level for protons and Fermi level for neutrons. So if we superimpose the, I don't know if you can see it because it's in green and probably it's not a good choice for the color, but this is the energy surface for Krypton 74. And you see this is the minimum of Krypton 74. We have one minimum here. And you can directly connect the minima that appear in the energy surface with gaps in the Nilsson levels, and these gaps are crossed by the Fermi energy, by the Fermi level.
So these added lines are already for a complete calculation. Right?
Yes. So this is, for example, the fact that you have here this minimum there in the prolate side is because there is a gap open here created by these G9 orbits, spherical orbits, and the orbits from the PF shell. And then the Fermi level of the neutrons here is crossing this big gap there. Okay. For the minimum here, the gap is basically this one, also in protons. In neutrons, sorry, in neutrons.
So what's the energy difference between between the two lines? Like you have this Fermi energy and the energy that you gain by minimization. Or, the blue and the red and black, the dashed line and the green line.
The green line, yeah, the green line is just a we are superimposing the energy surface.
Right, but that
so there is no scale in energy here.
Okay,
this is just a
Fermi energy that runs into the.
So this is just to say that the way you have or the shape you have in the energy surface is related also to a given underlying shell structure. So they are interrelated, so they are connected to each other. For example, in the case of lead-208, you have the minimum in the spherical point because your Fermi level is crossing the gap of 82 protons and 196 neutrons. And then that's why you have this minimum in the spherical point.
But you could have a gap in neutrons, but not at the same time in protons and vice versa.
Yeah, and then the minima will be more or less defined or well defined. Yeah. Or your energy will be stiffer or wider, so depending on the condition. Okay, so this is everything I wanted to say. I think concerning
just quickly. How do I know, for example, that the proton and neutron should have the same? They always have the same deformation, right? So just based on the arguments.
No, these are means. Yeah, this is the total. This is the mass, the quadrupole moment.
Okay. Oh, you're plotting mass, but my question is like that means the minimum in the beta for the proton, neutron, they always, they always happen, when one have a gap, the other also have a gap, right? Otherwise.
No, necessarily. No.
But we know, I mean, the overall deformation is always very similar between the proton, neutron, the final deformation.
Yeah, but the gaps depends on the, here.
I mean, the overall density of
Yeah.
of states has to be low. And it could be because of a large gap on the neutron side or on the proton side or on both.
You have also a Coulomb effect that depending on the Coulomb, you have the gaps for protons and neutrons that are different.
Okay, when you see this minimum of the beta happens when the Fermi energy is in the gap, this applies must be satisfied for both, so just
No, just for one species. If it is satisfied for both, then the minimum is deeper.
Okay,
That is the case, for example, for this double magic nuclei, where you have the. Okay. But this is a way of interpreting things, so it's not. I mean, so it's hand waving argument why we have this this minimum here or there. And the last comment, and I think maybe I could stop there and then go to for the symmetry restoration afterwards. I don't know, maybe it's better. Just the last comment. So this kind of minima here, that in our case, you see that this is because we are opening gaps in the Nielsen scheme and the Fermi level is crossing these gaps. Then if you represent this point here in the spherical basis, sometimes you get a perfect agreement with, for example, two particle, two hole excitations, or many particle, many hole excitations in the shell model language. So this description here, which is in fact describing quasi-particle vacua, so no quasi-particle excitation whatsoever in a given deformation. When you represent these states in the spherical basis, and this is what the shell model does, then these states are interpreted as many particle, many hole excitations. So it's a complementary description of what the shell model also uses for describing excited states and describing deformation.
So the many particle, many holes interpreted in the spherical equivalent.
Yes.
Right? Okay.
Normally, these are based on an underlying spherical shell model. I think with this, I can maybe because the rest is symmetry breaking and restoration.
We have 20 minutes.
We have 20 minutes left.
Yeah.
Okay, I thought it was 10 the last. Okay, sorry. Then I can continue.
Since we have more time, can we go back to the
This one? Or
the prediction of the deep? So is this measured or is this consistent with the experimental measurement? Is it verified by experiment?
This is something. In fact, this is something that I wanted to comment right in the symmetry restoration part because this is just an interpretation, and there is no observable whatsoever here. So we don't have any, except the mass and the radius, for example, the bulk properties can be computed in this way and this approximation.
But for the beta 2.
But for example, for the beta 2, we need observables. And which are the observables for beta 2? There are none. The observables are extracted. The beta 2 are extracted from B of E2s or from the energy of the 2 plus or the 4 plus, etc.
Right.
And here we cannot say anything about the angular momentum of the system. So this is.
I guess if I say it right, I mean these are the candidate states which you use to construct the final wave function.
Yes.
This already satisfies some very good things like quantum numbers and symmetries and stuff, but then they have to construct the final wave function.
So in fact, I just wrote this provocative sentence. I hope you agree with me or not. I don't know. So nuclear shapes comes as a non-observable degree of freedom or an artifact of the variational approximation at the mean-field level.
I would just tweak it a little bit. I would say it's not observable with the current experimental technology available, but in principle, it's observable by correlations. if you had multi-nucleon correlation observables, like multi-photon effects, you could see these things.
Yes, but then are we seeing this one body density?
You would have to do multi-nucleon correlations. So if you had the A-body density, you could say everything you wanted about the shape. By two-body correlations, you can talk about quadrupole moments, everything.
Yeah, but this is not the shape that is predicted by the mean field, I think.
Yeah, I mean, but I'm saying in principle, all these things are knowable. It's not that it's not knowable. It's just that the experiments don't exist to do this.
I think he's saying it's
But
more.
there are two issues, right? What this means, if you use the mean field language that you're presenting, then there's no nuclear shape that this current will, how you describe it, right? But that it may have totally different issues like what experimentally measured, because the connection can be field if you improve the model, if, for example, calculating a two-point correlation function or whatever. But the current, in the current approach, maybe there's no concept of
Why don't we let him explain to us how these
Yes,
mean field
sure.
states enter into
Yeah.
anything that can be actually measured?
Maybe another way of saying it is that these betas are not a property really of the one body density, but more of a correlation.
Yes, yes.
You can
But then, I'm sorry.
You can say that the size of the nucleus is also a correlation. Because actually, it's very, it tells you where one nucleon is related when you know where the other is.
Yeah. What I wanted to say here is that you want to solve the Schrödinger equation and the actual wave functions of the system are not just given by this approximation. And this is a nice way of parameterizing the actual wave function of the system. But we could have used another, and then shapes are not anywhere. No. So then, okay. So we already talked about the one symmetry breaking. It was the particle number symmetry breaking, because we are mixing protons and neutrons here. Sorry, particles and creation and annihilation of particles there. But also by imposing some shapes in the system, then we are also breaking other symmetries of the Hamiltonian. And by breaking all other symmetries of the Hamiltonian, what I mean is that so our Hamiltonian will commute with some symmetry operators. In particular, we will commute in the number of particles. We'll commute with the J squared, J set if they are rotational invariants, and you concept parity and so on and so forth. So as you said, we have to have simultaneous eigenstates of the Hamiltonian and all these operators. Okay, so and these are the solution, the exact solution of the Hamiltonian will contain these quantum numbers. Then from our mean field approximation, these wave functions actually are not eigenstates of these symmetry operators. That means that they are not like this. Okay. Therefore, a better approximation, and if we want to extract, for example, or we want to compare with experimental data where we know that we have states with a good angular momentum and parity, for example, and we are actually in left to 8 and not left to 8.5, then we have to restore the symmetries, and we have to build somehow we have to build eigenstates of the symmetry operators. And this can be done with these projection techniques. So we apply some operators on top of these mean field wave functions. And then by doing so, we build explicitly eigenstates out of these operators out of the mean field wave functions. And these projections techniques enrich the wave function in such a way that they are eigenstates of these operators. And they are not anymore mean field wave functions. Mean field wave functions in the sense that they are not anymore product of individual quasi-particles or individual particle on top of, or this product applied to a vacuum. So this is the way we build or we restore the symmetry. So, and this is something that we have to do in our theory because we cannot compare to experiment otherwise.
when you do this projection, you cut out certain parts of the state, which makes it no longer a solution of the variation principle, doesn't it?
Yes, but you can do the projection before or after the variation. So you can, for example, if you do, and this is what we do normally, we do projection after the variation. So that means that, as you said, the variational principle is not fully respected. So we will be above the variational solution of the projected energy.
But the results very different. If you do it in a different way?
I will comment on that. Yes. So these are typical examples for projection operators. So this is the, as you see, these operators are just producing linear combinations of mean field wave functions, because these are the phi will be a parameter of this linear combination, and these are this I to the phi n will be the coefficient of this linear combination, and then the mean field, different mean field wave functions are given just by e to the I phi and this operator applied on the wave function. Okay, that's why these new projected wave functions are not any longer mean field wave functions. So they are linear combinations of mean field wave functions. Parity and the angular momentum, you have to do this triple integral in the Euler angles to restore the angular momentum of the system, and these are normally parameterized by the Euler angles. So this is typical stuff, and I think Benjamin was commenting something about that. Okay, good. So this is the way we restore the symmetries, and let me show you some examples of how it works. So this is just again our magnesium 24. Now this is the beta gamma energy surface for the mean field solution here. And then when we restore the symmetry, then from out of each of these points here, we can build the different energy surfaces for different values of angular momentum. For example, angular momentum 0, 2, 3, 4, 5, 6, 7, etc. And then you see that this is the energy we get. This is not so the energy is normalized to the minimum of each surface. But typically for the ground state energy, for the angular momentum projection, we get some correlation energy of the order of 5 MeV or so. Okay, so we are gaining energy in the 0 class, even though in principle we could lose energy, but it's not the case for the ground state, for the 0 class, sorry. So we gain something like 5 or so MeV of correlation energy here. Obviously, for the rest of the angular momenta, then this is it depends on the system. Okay, so you see that we can produce for a single mean field energy surface, we produce many energy surfaces, each of them with a different angular momentum.
Did you mean 3 minus, 5 minus, or did you really?
In this case, yeah, this is something that it depends on how we build or how we break the symmetries in the mean field. So in this case, we are not exploring beta 3, and that's why we don't have parity breaking, and then we cannot produce negative parity states.
Is there a computational advantage of doing the variation principle first and then projecting rather than
it takes much longer if you do the variation after the projection than before the projection. Yeah. So these are just we take the minimum of the Hartree-Fock-Bogoliubov and then we project, and this is even computationally expensive for these interactions. But I think from the variational point of view, one should do the other way around. We should start from the very beginning with the projected wave functions in the variational space.
How would you actually do that?
Yeah, so you define your SAC. Instead of defining the SAC with phi, you define the SAC with P applied with this. And in fact, the let's say the variational parameters are the same because the same number, because what you are actually varying is the u and v's of this file.
So
But the projection, it takes a lot of computational time.
So you project from the single particle state first, and then you do the variation. That's what
Well,
you do.
the problem is you project all of the basis states in your bag before you start the minimization. Whereas with what you are doing, you are first minimizing and then you project only the minimum state.
Yes, that's right. Because if you want to do with the full variation before, so after the projection, so you project and you vary the project energy, then for each step of the solution of the iterative step of the solution of the Hartree-Fock-Bogoliubov equation, then you have to project and compute the energy and minimize the energy and the gradient and minimize the.
So correct me if I'm wrong, but to do this projection, you have to actually have a Hamiltonian, and
Yes.
you can run into problems.
Yes. In the case for, yeah, this is very subtle thing. So for the case for Gogny, if you use the remaining problem comes in the density dependent term, because the rest of the functional is a Hamiltonian.
Yeah.
Because we include baiting and all the chains. So in principle, we are safe from this. And if you use a given prescription for the density dependent term, then you are free of problems also. It is, yeah, but it is something that you have to take into account. Good. So this is just the
one question about
yes.
the projection.
Yes.
How do you know that if you take a minimum and project it, that this is still your minimum level? How do you know that if you have, for example, proof of your solution or your state and you project them that their minimal energy doesn't swap the order?
No, this is precisely what we have here. So for example, this is the surface that we project. And then we project to different angular momentum parity in this case, because in this case we are breaking parity, and then we can produce negative parity states here. So the minimum was here, but now the minimum of this surface, I don't know, well, it cannot be distinguished very much, but it's displaced a little bit. So yeah, so the surface changes. So maybe I can, well, normally. So imagine that you have just the beta 2, which is easier, and then you have something like this. This is your Hartree-Fock-Bogoliubov. And then whenever you do the minimization, sorry, the projection, imagine that this is the spherical point. Then the spherical point, since it's already an eigenstate of the angular momentum, then if you project to 0, essentially does nothing. So you get the same. And then you get something like this for j equals 0. Let's exaggerate this a little bit.
How do you go to lower energy by projection?
In the case of, because in this case, since we are dealing with systems that are even, then it is not variationally explored in the sense, but still we gain energy by the symmetry restoration.
From the projection, if you look at the how it's formulated, your state can be decomposed in a certain number of components, and you know, it's like just rationally, that there is at least one that is of lower energy.
Yeah,
Right.
so the variation states are not complete states.
Yeah.
And when you do the projection, you mix in states that you have not explored, and that can lead to a lowering. Does it always lead to a lowering of the?
There is at least one.
Yeah,
At least one of the
least one
states
state.
might be not the one you are interested in, but there is at least one.
so this is the, and then by projecting this wave function, we are extracting the different components of this deformation system, because this is a good basis for the many-body state. So for the many-body
This is why you think that any solution you get always have a fluctuation, because it contains many shapes components, right?
No, but the shape is here. Shape is here.
Shapes in the projected, but each of the point basically you get by apply weight, right? of the original space. Is that the case?
Say it again.
So what I mean, the final wave function is a superposition of.
Yeah, but
all-
this
all-
is this is coming after this.
Right.
Yes. Yes, that's the last step.
We have 1 minute.
Yeah.
but,
Yeah.
Okay.
If you just like to reply to your question, I mean, it's also one of the advantage of scanning different data, because even if you don't solve like the rational principle for the projected state by looking at different state with different deformations or different constraints, you will maybe find the minimum after projection.
Yeah, in this case, it's a kind of restricted variation after the projection. So this is variation before the projection. No, variation after the projection. So yeah, so this is another example. So I just showing you the projection of triaxial shapes. This is the projection of axially symmetric but quadruple and octuple shapes. And then the next step is the configuration.